This is going to be part 3 of my flat panel loudspeaker, distributed mode loudspeaker simulation program overview. And in this video, I'm going to talk about boundary conditions, or as Parts Express calls it, edge termination and damping. So when you make a speaker out of a panel, it has to be attached to something. It can't just be floating free in space. And the Parts Express guide has 7 different examples of possible supports that you can use to design these speakers. So they have rigidly suspended panel edges. That would be essentially where the panel edges are glued to something. And that keeps the panel edges from moving, and it keeps the panel edges from bending. So mathematically that means that both the excursion and the first derivative have to be 0, but the second derivative can be non-zero. If that matters to anyone. Okay, second thing is rigidly suspended corners with free edges. That's tricky to simulate. So how I simulated this was just make the exact corners unable to move, but their first derivative can still be non-zero. It's probably pretty close. I don't know. Suspended rigidly at a central location with free edges. So yeah, you just make the center of the panel unable to move. You can screw it to a pole or something. This one I didn't put in the simulation yet, but I can. And it's hard to figure out what they meant by this. Compliant suspension at a central location with free edges. What it looks to me is like they have the exciter here and then something here. I'm not sure what that is. But then in this part of the diagram, it looks like the exciter, the back of the exciter is attached to something. So I can do either one of those, and I might separate those out into 2 different in the future. I haven't programmed it in yet. But I can either have the exciter free and then some sort of compliant, like springy attachment around the exciter attached to something, or I can have the back of the exciter attached to a heavy support. Either one. The problem with some of these things is that attaching the exciter to something can often lead to the panel like breaking off or bending the exciter or something like that. Sometimes that works okay, sometimes it doesn't. So just practically, I don't know. Not always the best thing in the world. Okay, suspended rigidly at a central location with compliantly suspended edges. Yes, I can do that in my simulation. Compliantly suspended panel edges, so that's the same thing as this one, but without the central support. And then compliantly suspended corners with free edges. I'm just going to call that totally free plate. Maybe it's not exactly right on to a totally free plate, but just for the purposes of simulating this right now and comparing it to this, I'm going to call this a free plate and this a plate with its corners unable to move. So the first comparison that I'm going to do in my simulation is the rigidly suspended panel edges versus the compliantly suspended panel edges. So I'm going to use a real exciter. Actually, I'll use the heaviest exciter just because I haven't done that yet in a video. And the rigidly suspended panel edges will be clamped, 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 no stands. I'll do the same 0.2 meter by 0.3 meter by 6 millimeter acrylic panel that I've been using as my basic panel for everything. And let's take a look at these results then. There we go. Okay. Rigidly suspended panel edges, again, that's this. That would be where the edges of your panel are glued down so that they can't move and they can't bend, technically. But they can have curvature, second derivative, if that means anything to you. So one of the things about these this mode is pretty small, or like the excursion pattern is pretty narrow in space relative to the free edges or the simply supported edges, compliantly suspended edges, Parts Express would call it. Yeah, kind of neat. Okay, this is a big, heavy exciter too. It's pretty big relative to the panel. So we've got the coincidence frequency here at 6 kilohertz, and then the critical frequency where the dimensions of the exciter start to impact the radiation is at 8300 hertz. That's the blue line. Yeah. Okay, so let's compare that then to the SSSS, simply supported on all 4 edges, which is going to match this, compliantly suspended panel edges. Let's take a look. All right, cool. Dotted line is the results, acoustic radiation results, average horizon level acoustic radiation for the simply supported panel. And you can tell that the modes seem to be kind of similar but shifted down in frequency, and that's, I know mathematically that's exactly what happens. So this peak and this peak are the same shape roughly, although in the simply supported or compliantly supported edge termination case, this is broader in space. It's not like such a narrow shape. So yeah, trying to get closer to that simply supported edges will push the resonant frequencies down, which is always helpful. I don't think that either of these moved. Yeah, 8300 and 6000. I mean, the coincidence frequency can't move, but yeah, it doesn't look like the frequency where the exciter starts to impact the high frequency stuff changed either. You can see, this is kind of neat, you can see the big decrease in vibration output a little bit after this frequency where the wavelengths are equal. So that's what the exciter causes up here. It's kind of like a comb filtering effect. Okay, so that's a comparison of simply supported versus rigidly supported. So next I want to do the compliantly suspended panel edges here versus compliantly suspended edges with the central support here. So comparing these two together. So let's go back and let's just run this simply supported simulation again to get a fresh set of results without the clamped results mucking things up. Okay, so I'm going to compare that then to the compliantly suspended or simply supported panel edges with a center support. So that's going in now. All right, that doesn't look good. So the low frequency stuff has been mostly eliminated. We have a new big peak here at 396 hertz. Let's try to find that. Okay, so that's this radiation pattern. See, the center isn't moving because it has that stand. Then it looks like after about here, 3K, everything goes back to normal. Yeah, then it stops mattering very much that the center of the panel can't move. But adding that center stand definitely wasn't good for our low frequency response. We made the center of the panel unable to move, which is where all of our low frequencies come from. Okay, so I don't know. I wouldn't recommend that unless you're trying to go for some really specific sound. I probably wouldn't recommend that type of thing. Okay, next simulation that I want to do is comparing the rigidly suspended corners with free edges to the compliantly suspended corners with free edges. And these are maybe a little bit off from what I'm actually simulating mathematically. These are maybe a little in between. So this should probably be like clamped edges, where the edges are both unable to move and to bend. And this is where maybe, I don't know, these kind of look like rubber bands or something. It's hard to tell, but compliantly suspended usually means it can move, or it can't move, but it can bend. So, but I'm going to do this as totally free edges, and I'm going to do this as edges that can't move but can bend. So I might be off by a little bit, but we'll still do our best just to compare those two cases. Okay, so for the first one, totally free panel, no stands, that's going to match this case, supposedly. Okay, wow, look at that. Yep, these always look really good because they are good. This is a good way to make a panel speaker. They tend to have nice kind of broad omnidirectional radiation right up until about the coincidence frequency here. So, and then we have both the coincidence frequency and the critical frequency screwing things up as we get towards higher frequencies here. Yeah, so looks pretty good. Again, this might be a little unrealistic because you're gonna have to support the panel somehow. If you support it like from rubber bands at the edges, that's probably as close as you're gonna get to something like this, but it does look pretty good. This low frequency limit is going to be dependent on the actual exciter you use. The bigger and heavier the exciter is, the lower that low frequency limit gets. Okay, so let's compare that then. Again, that was this case to this case, rigidly suspended corners with free edges. And that means that I'm just putting corner stands on the plate. So let's look at that. Okay, so the dotted line then is the plate with the corner stands. This looks pretty good too. I mean, both of these are not bad. The corner plate one definitely has a set of sharper peaks and troughs at the low frequencies. Above about a kilohertz-ish, they're almost exactly the same. So it really only matters at the low frequencies which one of these you choose to use. Let's take a look at some of these things here. So like at 30 hertz, there's something going on. That's, yeah, that's that mode where the middle of the panel is bending out. That's omnidirectional radiation here, you can see. It's pretty much all omnidirectional up until 2 or 3 kilohertz, and then things start getting funky. Let's look at some of these other modes. So 400 hertz, it looks like there's something else going on. Oops. Where is that? Yeah, that looks like it's this mode. kind of a 3-1 mode. So, and then there's whatever's going on here, 100 hertz. Oh, that's interesting. That's where one edge of the panel is moving. That's kind of funny. Huh. Okay. Cool. Well, so both of these are pretty good, to be honest. They both have, I mean, honestly, the totally free one is maybe better because it's just flatter in here. But the free with the corner supports is not terrible either. Until they get screwed up here by the coincidence frequency and the critical frequency. All right, so then the last comparison I want to do is between the compliantly suspended corners with free edges and the suspended rigidly at a central location with free edges. So for that, I'm going to redo the totally free simulation so that we have a baseline. Okay, that was this again. We've seen that one before, and I'm going to compare that to this, suspended rigidly at a central location with free edges. So that just means that I put a center stand on the free edge panel. So we'll compare that to the previous results. Oof. Okay, I honestly had no idea what this one was going to look like. That is truly bizarre. There is, wow, huge swings in the frequency response from a big peak of almost 80 dB up here to down to 30, so 50 dB swings in the peaks and the troughs. So let's see what's going on up here at the peak. So at 88 hertz, we've got, yeah, the top and the bottom are moving. What's happening down here at the lowest, 176? It looks like it's just kind of unhappy. What's happening here at this peak, 227? That's where the left and the right side are moving. So the center here isn't allowed to move. So let's see. We've created a whole bunch of new modes that didn't used to be there. I don't know what's happening there at 980. Something funny is happening. Anyway, it's interesting. This is going to be a really unique frequency response. I bet it would sound really metallic. These really sharp peaks and troughs sound very metallic. I don't know how to describe it better than that. It would be a very unique sound if that's what you're going for. Probably wouldn't recommend it for like vocal reproduction. Could sound interesting with the right type of music, maybe? I don't know. Okay, so a lot of this too is going to depend on things like exciter placement, the materials, the length and width and thickness of the panel. So these metrics that we've looked at today are not independent from any of those other things, but this hopefully just serves as a good baseline for understanding what some of those mounting styles, what effect some of those mounting styles have on the sound of the speaker. Okay, so hopefully more videos coming soon as well.